Here's another example, and this time we have x squared plus y squared equals 100 and y equals 4 over 3x minus 18. The first equation you should recognize as the equation of a circle, and we can try to figure out what the radius of the circle is, since we know that the equation of a circle is x squared plus y squared equals r squared, and in this case we have r squared equals 100, which tells me that the radius of the circle will be 10. And this time I didn't do plus or minus because you can't have a negative radius, and so I only looked at the positive root, which is 10. Okay, so I know I have a circle with a radius of 10. Then I also have the equation of a line, and I know that the slope of the line is 4 over 3, and that the y-intercept is equal to negative 18. So I'm going to graph both of these and try to find the point or points of intersection between them. So starting with the equation of a circle, I'm going to use a scale of 2. So 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. Same idea this way. And so I'm just plotting the 4 easy points that I can use for the equation of a circle centered at the origin. I'm just going to draw the circle. And try your best to actually make it look like a circle and not a squircle. So there is my attempt at making a decent looking circle. And now I can draw the line. And the line has a y-intercept of negative 18 and then a slope of 4 over 3. So this is going to be negative 10, 12, 14, 16, 18. So here's the y-intercept of negative 18. And then I'm going to rise 4 and run 3. And as long as your horizontal scale and your vertical scale are exactly the same, you can actually just count boxes instead of counting units. And so because my scale is the same in this case, I'm just going to count boxes. So I'm going to rise 4 and then run 3, draw a point, rise 4, and run 3, draw a point, rise 4, and run 3 and draw a point. And I can draw my line. And what you should notice is that in this case, oops, I actually didn't rise and run properly. There we go. And what you should notice is that in this case, the line actually doesn't even touch the circle. So what that means is there are no points of intersection. Okay, there are no points that both this circle and this line actually share. Okay, so and this is part of the reason why it's important to try to draw your circle and your line accurately. Otherwise, if you drew a blob that kind of went around this way, and yes, that would be a blob, then you would end up having a point of intersection that actually doesn't satisfy both of them, and that's because your sketch of the circle or the sketch of the line may not have been accurate. Okay, so in this case there are no points of intersection or no solutions to the system. Therefore, there are no solutions to the system. Okay, let's look at another example. So we've seen an example where you had 2 points of intersection. We saw an example where there are no points of intersection. And let's take a look at what's going to happen in this example. So we have the equation of a line and we have the equation of a parabola. So this is the equation of a line, just a horizontal line. So y equals 2 is just a horizontal line. And then we have the equation of a parabola, which has been shifted to the left 1, shifted up 2 units, and has also been vertically reflected. And again, in this case, I can use a step pattern to graph this. If you're more comfortable now using mapping notation, you're more than welcome to. But in this case, I'm going to use the step pattern to actually graph the parabola. So y equals 2 is a horizontal line, so I'll start by drawing that. What that means is every single point on the graph has a value of y equal to 2. So it doesn't really matter what the value of x is. It means all the values of y will always be 2. Okay? And so I'm just going to draw a horizontal line. And I just realized that I forgot something very important in the last example that I did. So I'm just going to jump back to the last example. In this example, I would lose some communication marks because I forgot to label my equations. So please don't forget to label your two functions or your two relations. In this case, this is just a relation. Circle is not a function. And the equation of a line, which is a function in this case, don't forget to label them. Okay, so that's part of your communication marks. So going back to the example that I was working on, sorry about that. We have y equals 2, and then we have a parabola, which is negative x plus 1 squared plus 2. So I'm going to use a step pattern to graph this. So I'm going to plot my vertex, which is at negative 1 and 2, and then use a step pattern to graph it from there. So negative 1 and 2. And you'll notice that the graph and the parabola and the line have already intersected. And then from here I'm going to move over 1, down 1 since it's been reflected. Go back to the vertex, over 2, down 4. Back to the vertex, over 3 and down 9. And then do the same thing on the other side. And sketch the parabola. Okay, and again, don't forget to label it. So y equals negative x plus 1 squared plus 2. And what you'll notice is that these two equations only have one point of intersection, and that point of intersection in this case is at negative 1 and 2. It's right at the vertex of the parabola. Okay, so the line just touches it right at the vertex and then it continues on its way. So therefore, the solution to the system is negative 1 and 2. That's the only point that both the parabola and the line actually share. Okay, so that's the only point of intersection. So we've looked at an example where there are 2 points of intersection, no points of intersection, and just 1 point of intersection. So now we're just going to summarize that. And so linear quadratic and linear circle systems of equations may have no solutions, one solution, or two solutions. No solutions would mean that the circle and the line or the parabola and the line would never touch. So that's an example of when you have no solutions. One solution means that the graph barely touches the line barely touches the curve, or in other words, it touches it at just 1 point, or just like we saw in the last example, it touches at the parabola at the vertex, or along 1 point only. So there's lots of different ways that this can happen, but it's just to recognize that you can have 1 point of intersection where the line just touches the curve and then it continues. Okay, you could also have a vertical line for a parabola as well. Okay, any vertical line will touch the any vertical line will touch a parabola at 1 point. Okay, you could also have a for another example for a circle, you can also have a circle that has a horizontal line that hits it at the top, or even a vertical line that hits it along the edge. Okay, so there's lots of different ways to have one solution. Two solutions, well, that just means that you'll have a circle and the line will cross right through it and touches the circle at 2 points, or you can have a parabola and have a similar idea. Okay, it goes right through it and hits it at 2 distinct points. So the only options that you have for a linear quadratic or a linear circle system of equations is to either have no solutions, one solution, or two solutions. And so the one that we might want to question is, why can we not have an infinite number of solutions to a linear quadratic system of equations? So why can we not have an infinite number of solutions to a linear quadratic system of equations? And the answer to this is pretty straightforward. One equation is the equation of a line, and one equation is the equation of a curve. And there's no way that a line can overlap with a curve. Okay? So I'll write that down. So one equation represents a line, and the other equation represents a curve. Since a line and a curve will never overlap, therefore, we cannot have an infinite number of solutions.